All right, this is a question that I wanted to do yesterday, and then never got to. Okay, and this goes over okay, no, and there's one after this that I want to do on titrations also. Okay, so a 0.1276 gram sample of an unknown acid was dissolved in 25 milliliters of water and titrated with 0.0633 molar sodium hydroxide solution. The volume of the base required to bring the solution to the equivalence point was 18.4 milliliters. So let's start with what is the molar mass? Okay. Let's see here. So how would you start answering, what is it that I need? If I want to find the molar mass, what do I need?
Grams per mole.
Good. Do I have the grams?
Yes.
Yes. Do I have the moles?
No.
Okay. So that's what I need to find, right? I need to find the moles. How am I going to find the moles? Well, molarity.
Or molarity.
Okay, so I'm doing a titration. Can I find the molarity of the acid if I titrate it with the base? I can. Because whatever the molarity of the base, the moles of the base that I added equal what? The moles of the acid. Okay? So this will work out. Okay, so you can use the titration equation, molarity of the acid, volume of the acid equals molarity of the base times the volume of the base here. To find, to find the molarity of the acid if you wanted to, or you just simply need to find the moles of the base because the moles of the base equal the moles of the acid. So molarity equals moles over liters. So for the base, I used for this titration, I used a 0.0633 molar solution, and I titrated it with 18.4 milliliters. So the moles are equal to the molarity, which is 0.633, times 0.0184 liters. Okay? So I convert the milliliters to liters, and I will find the number of moles. And then I simply need to take the moles of the, the grams of the acid and divide it by the moles. Well, the moles of the base equal the moles of the acid because I have reached the equivalence point. It absolutely does because H plus plus OH minus equals H2O. I've neutralized H plus with OH minus. H plus plus OH minus produces H2O. The moles, I need 1 mole of acid for every 1 mole. This is a monoprotic acid. Okay?
We don't know that they're equal in the beginning, do we?
Yeah, that's the whole purpose of a titration. The whole point of a titration, the reason it works so well is because if I titrate an unknown acid with a known base, I can determine the molarity of the acid because it will equal, I can determine the moles of the acid because it will equal the moles of the base that I add, because they will react with each other to form water. Okay? So that's the whole reason these titrations work. So in the laboratory, we go in the laboratory and we perform a titration to determine the molarity of an unknown acid simply because the moles of the acid equal the moles of the base. That's our reference. So yes, that's why we can use this equation right here. MAVA equals MBVB, because as you can see, moles equals molarity times volume. So the moles of A equal the moles of B. Okay? So what here in this case, if I find the moles of B, that's the moles of A. And I just simply have to take my 0.127 grams and divide it by the moles. So did anybody find out grams per mole?
Yeah, it's 0.0011. I found the molar mass.
That's the moles?
Yeah.
Okay, so that's the moles, 0.00116 or something?
Yeah, multiplied by the grams per mole.
Not mole, no. You just take the grams, divide it by the moles.
Oh, yeah.
And that's your grams per mole. So what is the molar mass of this unknown acid?
Oh,
110. 110. The molar mass of this is 110. Good. Grams per mole. Okay. So then, if we wanted to identify this, what this thing is, we have a reference. We know it's molar mass, so we have some information about it. Okay. So we have 0.1276 grams of unknown acid. Okay. And we have the moles. Did you figure out the moles of the acid? I'm sorry?
No, that's probably why I don't have any answer.
Okay. So it was something like 0.00. Okay, just 2 zeros. Okay, and that's how I'm going to figure that out. Sure. Okay. So the way I got the moles is that I took the molarity of the base, which is 0.063. Okay, so molarity equals moles over liters, and the moles equals molarity times liters. So the moles here is equal to the molarity, which is 0.0633 molar times the liters, and I have 18.4 milliliters of base that I use to titrate this with, and the base molarity is 0.0633 molar. Okay, so I convert that to liters. Okay, and that's going to equal 0.00116 moles of base. The moles of the base are equal to the moles of the acid. Okay, so that's how I get this. Okay, so that's that first. They're saying A, what is the molecular mass of this grams per mole. That's how I would determine that. Okay. Let's see. A few boxes here.
So your N1V1 equals N2V2, you just did it twice because it's the same. So either mole A is equal to mole B.
Moles of A equals moles of B. So that's why MAVA equals MB Okay, but in this case, we didn't really need to do that because we weren't looking for the molarity, we were looking for the moles. So that's why we just solved for the moles instead. The moles of the base. We just went ahead and solved for the moles of the base, which equals the moles of A. The moles of the base that I add are exactly the same as the moles of the acid that were there, because once I reach the equivalence point, I've neutralized the solution, right? So that means I've added exactly the same number of moles of base as there was acid there to begin with, to neutralize it. So in a titration, if you remember from doing these before, you're sitting there, you have your burette, you're dripping in base to your acid. And you're sitting there and you do it by drop until it turns color, pink or whatever, and then you shut it off, and then you read your burette. This is exactly how much I used, okay, of my base. How does that relate to my acid? Well, it relates because exactly the amount of moles of base that I use are exactly the amount of moles of acid that are in my acid solution. Okay, the moles of the acid equal the moles of the base. So H plus OH minus produces H2O, neutralization. Okay.
What was the second question?
Okay, so this one's a little more involved. Guys, that's an easy question. Okay, grams per mole, right? Find the moles of the acid. Okay, so here, what is the Ka? So we're looking for the acid constant of this thing that we just titrated. What is the Ka if the pH 5.87? If the pH of 5.87 after adding 10, if your pH is 5.87 after adding 10 milliliters of the base. Okay. So my pH is equal to 10 point. I'm sorry, 5.87. Thinking of a different question. 5.87. Okay. And I added 10 milliliters of base. Okay. And this is a monoprotic acid. So HA dissociates into H plus.
What is monoprotic
Did you
acid
just,
mean?
I mean, is that just assumed if it doesn't say it's not?
It says it in the question. I didn't put it in that.
Oh, okay.
But it does say it. Okay.
What's a monoprotic acid?
It means there's only one hydrogen. Instead of being H2A, it's HA, which is going to be, I would just assume it is a monoprotic if they don't tell you. Okay. That would be diprotic H2. And remember, I told you we'll look at an example of finding the Ka using two different Kas to find the concentration of something. Like that. Okay. All right. So here we have HA dissociates into H plus A minus. Okay. These initially are 0. We know that. This is plus X. This is plus X. And X and X. The initial concentration of the initial molarity is determined because we have 0.1276 grams of this thing. dissolved into 25.0 milliliters. Okay, so how am I going to find this number that goes right here? It's going to be minus x. Now we have the molar mass. What can we do with that? Find the moles. 0.1276 grams divided by 110 grams per every 1 mole of it. Okay, so what are my moles? Say it louder, I'm sorry. 1.16 negative 6 3. Okay, thank you. Moles. And then how do I find molarity? Moles divided by 0.025 liters. Okay?
The moles that we use here is the same as the moles of acid that we calculated before, right? Because we got 0.0011.
Yes, it is. That's true.
So we don't have to do that anymore?
Not necessarily. If you make that connection, you could go back to it. Okay, that's right. Okay. So now we're going to take the moles divided by the liters. Okay, we had 25 milliliters, so 0.025 liters. What's the molarity here? 0.0464. 0.0464. Okay, so this is where I'm starting. Now, they want me to find the Ka. What does that mean I need? What do I need to find the Ka?
Concentrations and equilibrium.
The equilibrium concentrations. I need all of these numbers down here, right? So how am I going to find them? What did they give me to be able to find these numbers? They gave me the pH. pH is equal to the negative log of the H plus ion concentration. So if I take the anti-log of the pH, it will give me which of these?
H plus.
It's going to give me H plus, which is X. And then I can fill in X here, and I'll have all those numbers, right? And then I can easily find my Ka. Okay, so what is X?
1.35 times 10 to the negative 6.
1.35 times 10 to the 6.
How do you know it's?
Okay, and this number is going to essentially round back up to what it is in the beginning. Okay, so these are our concentrations at equilibrium. Ka equals 1.35 times 10 to the negative 6 squared over 0.0464. Products over reactants. So what is my Ka?
3.93 times 10 to the negative 1.
Okay, so this is a terrible acid. Okay.
So I know you got the concentration of H plus, but why did you put it in for all the X's again?
Okay. So the reason I put it there is because H plus, the concentration at equilibrium is this. And so if that number is this equilibrium concentration, that means it must be X, because this was just simply 0 plus X, and then give me this number. So then I can replace all the X's with that number. and I'll find my equilibrium concentrations.
Thank you.
And then you just drop the.
Go ahead. What?
So you don't subtract the negative 1.35 into the 6 because it's a small number and it's less than 5%. So you drop it.
Yeah. Drop it. Okay, let's do another fun one. So a 25.0 milliliter solution of 0.100 molar HCOOH and a 0.10 molar AOH solution. Whoops. Sorry, I was writing two different questions. Okay, so 0.01 molar acetic acid, CH3COOH, is titrated with a 0.200 molar KOH. Okay. It's molar. What is the pH after the addition of A, 0.0 milliliters, B, 5.0 milliliters, C, 10.0 milliliters, D, 12.5 milliliters, and E, shoot, and E. Okay, so after I have a 0.1 molar acetic acid solution, I'm titrating it with a 0.2 molar potassium hydroxide. What is the pH after the addition of these amounts? Okay, so we have, I'm just going to do the general acid, J into H plus OH minus, I'm sorry. HA plus OH minus into Okay? So this is the titration equation that we're going to use, and then we're going to use Henderson-Hasselbalch to calculate the pH after
Is this
the amounts.
this is the base constant, H, or that equation right there that you used? It's just the weak base.
That's just a weak acid reacting with a base. Okay? It's an acid. It's the acid, because if I'm adding sodium hydroxide, what is it reacting with? It's reacting with the acid, right? So I start with the acid, react it with the sodium hydroxide, and it's going to give me water. Titration is H plus OH minus produces water, and you're left with the conjugate base. Okay? This is important because that's going to establish the pH in the end, okay, at neutralization. So let's see what we have.
So because it's a weak acid, you put HA? Because last time you just put H plus OH into water for titration.
Yeah, because we want to see the conjugate base that's produced. If it was a strong acid and a strong base, I could just do H plus OH minus produces H2O.
So every time we do a titration with a weak acid and a weak base, we use that?
Sure. Weak acid and a strong base,
Weak acid.
okay, which is a titration. Okay, so 0 milliliters. 0 milliliters. I'm not adding any sodium hydroxide, okay? So this thing is going to start out at 0.1 molar of HA. So actually, let's save this for step 2. Okay, for when we actually add some sodium hydroxide. .1 molar, 0 minus x plus x. We get x, and 0.1 minus x. Drop the x, right? And then Ka. Okay, so this is just a simple. What is the pH of a 0.1 molar acetic acid solution? Okay, Ka equals x squared over 0.1, right? And hopefully you're getting to the point where you can recognize that that's pretty much what it's going to be every time for these weak acids. Okay, to find x, it's going to always be x squared over whatever the molarity is. X squared over the molarity because you drop the x. Okay, the Ka for acetic acid, Ka equals 1.8 times 10 to the negative 5. Okay, so we're going to take 1.8 times 10 to the negative 5 equals x squared over 0.1. So what is x here? X equals what? It's right here. It would be given to you. 0.013. So that's my H plus ion concentration, right? So what is the pH for A?
What is it?
1.9.
1.87.
That doesn't sound. Oh, it's 0.00. Acetic acid shouldn't be that acidic. 35. it should be this 0.0013. Yeah. And then 2.8.
2.87.
Yeah. Okay. So that's what it should be. pH of A equals 2.87. Okay. All right. So that's a pretty basic. What is the pH of an acid at this molarity?
How'd you get the 2.87 again? The anti-log of the
So X is the H plus ion concentration. So I take the negative log of this, the negative log of 0.0013, and that gives me 2.87. If I take the anti-log of 2.87, it gives me this. Yes, ma'am?
Isn't the milliliters are equal of KOH, like after division of 0 milliliters? What?
Yeah. So we didn't add anything.
Yeah, but what is it when you do add the
It's
KOH?
5 milliliters. It's milliliters. 10 milliliters of KOH, of 0.2 molar KOH.
Okay.
Okay? That's what we're adding. Okay, so let's see how we do it when we add 5 milliliters of KOH. Okay, so we have HA plus the sodium hydroxide that we added is going to give us H2O plus A minus. Okay? So this is 0.1 molar. This is 0. Oh, I'm sorry. I'm already messing up. Okay, so our initial concentration is dependent on the dilution because we started out with 25 milliliters of a 0.1 molar solution of acetic acid. And then we added 5 milliliters of a 0.2 molar potassium hydroxide. So we have to figure out the dilutions of everything that we're starting with. So let's do that. So we have, for the acid, M1V1 equals M2V2. So we have 0.1 molar times 25 milliliters that we're adding, 25 milliliters, equals my new molarity times the volume, total volume. I added 5 to 25, so what is that? 30 milliliters. So I'm going to take 0.1 times 25 divided by 30. My new molarity is what?
0.083.
Okay, now for the base, I start out with 0.2 times 5 milliliters equals my new molarity of the base times 30 milliliters. Okay, so what is the new molarity of the base? Three, like that? Okay. Go ahead, ask it. What?
The second equation.
This one?
Yes.
Okay, so that one came from this. The molarity of the base is 0.2 molar, and I added 5 milliliters of it. Okay? And the final volume after I add that to 25 milliliters of the acid is 30 milliliters. Okay? So we get this. 0.2 times 5, M1V1 equals M2V2. Okay? This is for the acid. This is for the base. Okay. This is at 0. We don't care about the water concentration or anything about it, so it's just there to show us our equation. Okay? Now, this 0.033 molar hydroxide is going to react with the 0.083 molar HA. Okay? So minus 0.033 minus 0.033. This goes to 0, and this is plus 0.033. Okay, so what does the HA become?
0.05.
Okay. How do I solve for the pH at this point? Okay, so with the titration, what I want you to realize is at this point, to find the pH, I can simply use Henderson-Hasselbalch. Okay, base over acid. Base over acid. Okay, otherwise, this is how I would set it up otherwise. Okay, I would set up HA dissociates into A minus plus H plus. Okay, and I would have the concentrations of 0.05 and 0.033. Okay, and this would be minus x plus x. This is 0, so this would be plus x. Okay, and then I could set up for the equilibrium equation. But I drop all the x's and things, and so it ends up being that solving for H plus here simply ends up being the Henderson-Hasselbalch equation.
So
Okay.
going back up there, why did you write 0.033 across all the way down? I mean, like all the way across.
Because that's the amount of hydroxide that's reacting with the acid. I have 0.033 molar OH minus. That's what I just determined, right? It's going to react with the 0.083 molar HA. And one of those two things is going to go to 0, the one that's in the lesser amount. So which one's in the lesser amount? OH minus. So OH minus is completely gone, and 0.033 of it reacted because 0.033 of it reacted with the HA. So that's how much HA I'm left with. Okay, and when that reacts, when OH minus reacts with that, I produce 0.033 of the A minus, which is my base. So now I have a situation where I can use Henderson-Hasselbalch because I have base and acid. So pH equals the pKa plus the log of the base over the acid. The Ka equals 1.8 times 10 to the negative 5. So pH equals 4.74 plus the log of 0.033 over 0.05. So what is my pH here? And it should be lower than the pKa, right? Because it's more acidic. There's more acid than base. So 4.56 is my pH. Okay. Now I want you to try to do I want you to try to do it now with C, 10 milliliters. Okay? So what is it if I add 10 milliliters instead of 5? So I'll leave this up as a reference. And now what happens if you add 10 milliliters of the base instead of 5 milliliters of the base? Say it again, I'm sorry. That's right. So find the molarity of the acid, find the molarity of the base after the dilutions. So do M1, V1, M2, V2 for both the acid and the base again, because now it's 25 plus 10. That's 35 instead of 30. So do your M1, V1. V2 is 35 this time instead of 30. B1 is 25 for the acid. For the base, it's 10. V1 is 10. What happens if what? Is if what's equal?
Concentrations.
If the acid and base, you tell me. pH equals pKa plus the log of the acid over the base. pH is equal to, huh? pH equals pKa. If the acid and base concentrations are the same. I don't think we're there yet, right? Yeah, I don't think so. That's too low. This time it's going to be more base over acid, and so it should be above 4.76. Okay, what did you guys find for the concentration of the acid in this case? What's the new concentration of the acid? Okay. And for the OH minus base? Okay, so minus 0.0571, minus 0.0571, and this is a 0 plus 0.0571. 0.0571. We already know what our pKa is. Get rid of this. This is 0. What's the HA? Like that? Okay. Say it again. HA is 0.0174. Is that what you said?
No, the last one, just change it to a 4. Yeah, instead of a 1 to 4. 714. 0.0714. Yeah, the top number.
Yeah.
Top number.
Oh, this?
Yeah.
You just gotta make sure you also subtract the base as well.
So that's right there?
Yeah.
Okay.
My bad.
Anyways. All right. So now I'm just going to take my same Henderson-Hasselbalch base over the acid. So now I have 0.0571 over 0.0144, okay, or whatever you guys got for that number, okay. And then my pH comes out to be what? Okay. So this time I am over my pKa because there's more base than there is acid in the ratio. More base than acid. So my pK actually gets added to. Okay? Actually add to my
There's more base in this one. Because of your conjugate base, and then your acid.
Okay, now the next is 12.5. Now do it with 12.5 milliliters. 12.5 milliliters of KOH.
What was the last thing you said on the last slide? We got the pH. So after we get the pH, there was more.
There's more base than there is acid. So that's why it gets added to the pK, which is 4.74. So this pH is above 4.74 because there's more base. If there was more acid on the bottom, if this bottom number is bigger, then it would get subtracted from the 4.74, which is what it was in this case. See how it's 4.74 and the pH is 4.56. That's because there's more base, or sorry, more acid than there is base. So here it gets added to the pKa, here it gets subtracted from the pKa because of the ratio. So if I take 0.033 divided by 0.05 and then take the log of it, I'll get a negative number. If I take 0.0571, I'm sorry, 0.0571 divided by 0.0144 and I take the log of that ratio, it's going to give me a positive number. So don't forget the log log right here. Take the log of that ratio. It'll give me a positive number. And then so I add it here and I subtract it.
So if you get a positive number and then you add it to that.
That's right. And so the pH is increasing. Here the pH is decreasing. So that's just a quick check that I did this whole thing right. If this number is bigger, I should have a bigger pH. If this number is acid is bigger, I should have a smaller pH than my pH.
How does it go down when you add base? Because right now the pH is 5.4. That's what I was.
Sorry, go ahead.
You just added 2.5 more milliliters of base. seem right, right? The concentrations equal each other. Did anyone else get that? They both equal 0.0667.
Okay, but good. Okay, so there's one other thing we have to consider there.
Oh,
All right?
why? Part of
Let me show you.
Wait, are you talking about the concentrations of
Yeah.
12.5? Oh, okay. Yeah, I'm like, wait, what?
they equal, right?
Yeah, 0.667.
Okay, what do we call it when the acid and the base concentrations neutralize each other? We've reached what point?
The equal, no, the
In a titration. This is a titration. That's a whole, what am I trying, in a titration, I'm trying to reach what point? The equivalence point. I'm trying to reach the equivalence point. Okay? Did you say, I thought you said equilibrium.
Oh, I did, my bad.
Okay, so equivalent.
They're the same thing.
No, they're not. Okay, so I'm trying to reach the equivalence point or the end point of the titration. All right? So HA is what in this case?
0.0667.
These are the same, right? Okay?
Okay, got it. Which means they completely dissociate. So,
Okay, so at the equivalence point, this is what I have. This is my situation. So in this case, I am not going to use Henderson-Hasselbalch because I do not have acid and base concentrations, right? I don't have any more acid. All I have is what? I have a weak base. Now the question is, what is the pH of a 0.0667 A minus?
It'd be the POH.
So I say A minus, A minus plus OH minus, I'm sorry, H2O. They will be. Produces HA plus OH minus. So consider this question now. What is the pH of A minus? Or in this case, this is acetic acid. HA is acetic acid. It produces acetate. What is the pH of a 0.0667 molar solution of sodium acetate? That would be the question. What is the pH of a 0.0667 molar sodium acetate, sodium CH3COO? Okay, solution. Here's my sodium acetate. The sodium goes off. It's a spectator ion. It reacts with water. It produces acetic acid in solution plus OH minus.
So we just went back.
The only thing that's left is that base. That's what's going to produce. Okay, so if I react a strong acid and a strong base together, the pH at the equivalence point will be 7. But if it's a weak acid with a strong base, at the equivalence point, I will have some weak base left over. That weak base will establish an equilibrium, and it will be what determines the pH of that equivalence point. Okay? It's not 7 because it's a weak acid that I'm titrating. So it has to, this base will establish its equilibrium. Okay? So this is 0.0667. This is 0, and this is 0. Minus x plus x plus x. Okay? In this case, Kb equals x squared over 0.0667 minus x, but we'll drop that, okay, here. So remember, this is a basic question. Hopefully you're recognizing x squared over the molarity. X squared over the molarity. KB equals x squared over the molarity. Okay? And that's where I go from there. Do I have my KB? You can find it. So find it. Find your KB.
Divided by the 1.8 or 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5.
That's right. KW is always on top. So here I'm going to find OH minus, right, is X. That's going to give me a POH, and from the POH I can find the pH. Okay? So, so my pH here is what? That's right. That's right. Okay, so that's my pH. That's what you should be getting to. Yes?
Oh, I'm just stretching.
Oh, okay. I know that a problem like this will do that to you.
Wait, so you got the pH by taking, it was 0.0667.
So did you find out what X is here? What's X?
Well, I had it, but mine's not.
5.56 times 10 to the negative 10.
Okay, so that's KB,
Yeah, that's good.
right? Okay, so that's your KB, and then X is what? KB times this, divided, take the square root, that'll be X.
6.08 times 10 to the negative 6.
Okay, this is your OH minus ion concentration. Take the negative log of it. That'll be your,
The OH because KB, that's how you get it. We got it from KB because it's the base constant.
yes,
Okay.
and because we have OH here. So X is the OH minus, okay? So this X is my OH minus ion concentration. I take the negative log of it. That'll be my POH, okay? So the negative log of this equals my POH, and then I can find my pH by subtracting it from 14. You guys seem angry about this question. Huh?
It's not the math is the kind of simple. It's just setting
This equation?
Everything is different. It's like this creates equilibrium and this, and then it goes back. It's just every time it's different. There's no way we can remember all that.
These are
See,
recorded.
there's
No,
yes,
I
this
mean, every single one is different.
So, if you have,
It doesn't matter. Each question, there's no. It's not like a single scenario. It's like every. I don't know. No, it's not. Where were you yesterday?
I mean, 14 minus, okay.
What are we doing when?
okay, so then you're really going to like the next one.
No, what happens? The base is more now.
Exactly. And you're going to love that. Okay?
Oh,
You're going to love that because it's super easy. Let's do this next one and then we'll take a break. Okay?
Wait, what did you say that we're going to love what?
You're going to love the next scenario. Okay? Okay, 15 milliliters. No, I'm being serious. This one's easy. This one's easy, okay? This is the easiest of all these scenarios, okay? 15 milliliters. I'm going to add the 15 milliliters to the 25 milliliters, okay? So some of you have already done. Shoot, come on. I know. Okay, so HA plus OH minus produces H2O plus A minus. Okay, so what is the HA concentration for the last scenario? Like that?
Yes.
Okay. 0.075. Okay, now, which one's less this time? The acid. So this one goes to 0, right? This one, 0.075, is minus 0.0625. What does that become?
0.0125.
Take the negative log of that. What's your POH? Don't even worry about it. You don't have to. Once you find that you have excess of the OH minus, that's your POH. Find your POH. What is your POH? 1.9. Okay, so pH equals 12.09. You're done. Okay?
So why did you use those numbers? Why are they the same numbers? Are those just the
This is the next scenario with 15 milliliters.
so this is just the answers for that? You just worked out you skipped all the work and that's what you came up with?
Yes.
And then okay.
So if you did the dilutions, M1 V1 equals M2 V2, you would find these numbers. Okay? This is greater than this one, so this one goes to 0 this time. You have leftover base, 0.0125. So because I have extra OH minus in solution, that's going to determine my pH. So the POH of that is 1.9, and the pH is 12.09.
So when you have more base acid that determines the pH.
When you have leftover OH minus in solution, that's going to determine the POH of your solution, which will determine the pH. Okay, see? There you go. That one's not too bad, right?
That's
Oh,
the
that one.
only ones that are going to be on the test, right? Damn, this test isn't even for a couple weeks even.
The final is comprehensive, guys. The final's comprehensive. So one question for like the last 3 chapters. You know, I wish I had better news. I mean, a 5-week class, guys, it's just.
It's still gonna be on the computer, right? So the good news is you still have a chance. Only there's a chance. Plus you're just really bad at guessing.
Okay. So let's we can take a break now.
Well, no.
10-minute break. We'll come back. What's that?
It's just 15.
Say it again.
It's 13.02. It's negative log.
Oh, I didn't calculate. So what is the POH?
Because I got the negative log of 0.0125, and then it was
Did I mess it up?
0.97. It's negative log.
It's 1.90.
No.
It is.
I have it on my haircut right here.
Negative, right?
Yeah, I'll figure it out.
What did you do?
No, hold. So did you take the negative log of 0.0125?
Yeah.
Yeah.
What is it? 1.9.
I'll do an anti.
Okay. And then 14 minus 1.9.
Okay. I was like, oh man.
Confusing. My bad.
Okay. That's why you need a break. Well, there's multiple parts to that question. Let's do a few more examples here. Okay. Sure, we'll start with this one. Okay. So there was a question on the homework you guys had that I want to clarify how to do this type of question. Okay. H2SO4, hydrosulfuric acid. I'm sorry, sulfuric acid. Is it hydrosulfuric or sulfuric?
Hydrosulfuric.
Oh, I'm sorry. And then it's asking for the concentration of sulfide. Okay, I'm sorry. So H2S, and we want to know the concentration of S2 minus. Okay. So to do this question, okay, the answer to this question is very simple because it's staring you in the face. Okay, but we're gonna see why. All right, we're gonna see why. The answer. Okay, so H2S is. Did it give me a concentration of it? 0.1. 0.1 molar. Okay. It's 0.1 molar H2S, 0.1 molar. Okay. This dissociates into HS plus H plus. Okay. So 0.1 molar. This is 0 and 0. This is minus X minus X. This is I'm sorry. This is minus X. Minus X plus X plus X. Okay. So then we can find out what X is. That's what we need to do because the Ka here equals X squared over 0.1 minus X. So we can solve for the for X, and really we could probably go ahead and make the assumption of dropping X here because it's the Ka is so small compared to 0.1 molar of a solution. So what is X here?
We're using Ka1.
Yes. Ka1, because that's for the first hydrogen.
7.54.
So if you have 2 Kas,
7.55 times 10 to the negative 5, right? Okay, so that's what I'm getting here for this, 7.55 times 10 to the negative 5. Whoops.
Did you use the K2, Ka2? Oh, we used Ka1?
Yes, because it's for the first hydrogen. Ka1 is for the first hydrogen that comes off. Okay?
Is that equilibrium? Is that supposed to be?
And this is going to be 0.1 molar approximately. Okay? Because minus x will just round back to 0.1, right? Okay, so this is our first equilibrium. That's what we have in equilibrium at first. Okay? Now let's look at the next equilibrium. So in the next equilibrium, we're taking HS dissociates into H plus S minus. Okay? And we're starting with 7.55 times 10 to the negative, what was it? 5. Okay? And these are 0 again. Okay? I'm sorry? Oh, I'm sorry. And this is 7.5.
Why is it?
That's what H plus was in the, right? That's what
Wait, so what is this, like, what are you doing right now? What is this equation?
that's what we have to start with, right? These are the initial concentrations of the second situation.
We never had H plus in the first. We did.
Sure,
Oh,
sure
yeah,
we did.
I'm a liar.
Yes, you are.
But that would be the same in the second equilibrium, too?
For K2?
These are the initial constant. This is initial, right? This is I. This is not equilibrium. This is initial of the second situation.
Second. Yeah.
Okay? So, I'm sorry, Andrea, what was your question? I didn't mean to ignore you.
Okay, so you said the second situation, is that like K2 or?
Yes, now we're going to use K2. That's right. Okay? So, now in this situation, we have 7.55 times 10 to the negative 5 plus x, and 7.55 times 10 to the negative 5 minus x, and then we have x. Okay? So 1 times 10 to the negative 19 equals 7.55 times 10 to the negative 5 plus x, but we're going to drop that because it's insignificant. We're going to make that assumption. I mean, look at the Ka for this is to the negative 19. It's very small. Okay? Times x. It's not x squared because now we have an initial concentration here. In the earlier situation, it would be x squared because it was at 0. H plus was at 0 initially. Okay? Divided by 7.55 times 10 to the negative 5 minus x. Drop the x. This cancels, right? What does x equal? What is the concentration of S2 minus in this solution? 1 times 10 to the negative 19, which is the Ka of the second situation. Okay, so that's my answer right there. So if they're asking for the ion concentration of a diprotic acid of the of S2 minus or whatever it is, SO42 minus if it was sulfuric acid.
What was the X for K2?
X equals the Ka,
That's gonna be the same every
the Ka2. So it's always like that. If they're asking for not the H plus, if they're asking for the ion concentration of the second of the ion, the anion of the anion of the acid, since it's a diprotic acid. It would be the exact same situation if it was for PO43 minus whatever Ka3 was. If it was for H3PO4, whatever Ka3 is would be equal to the concentration of PO4 3 minus. Exactly. You don't have to do this. This is just showing you why it is that it does that. Okay? You could read this question and answer it right there. If it's asking for the anion, S2 minus here, it's 1 times 10 to the negative 19 is the concentration of the anion in this solution.
This is what we use for the second equation.
So x is 1 times 10 to the negative 19, so it's on the next slide. So
It is.
wouldn't you just divide 1 times to the 19 divided by 7.55, and that's how you get the x, or you would
Okay, so do you see here that it's this times this divided by this? These two things are the same, so they cancel. And I'm left with x. X equals 1 times 10 to the negative 19.
So you wouldn't divide 1 times to the 19 with the 7.55?
Nope, they cancel. They're gone.
Oh.
So you're left with x equals 1 times 10 to the negative 19. It's another one of those beautiful, easy situations. It is. It's that easy. And it's even easier than that because in the beginning they gave you the answer right here. Okay?
And then this is what's left, so HS H plus S. And then we plug the X in.
Okay? Any other questions about that? I just want to clarify. You're not going to have anything more difficult than that for diprotic acids. Okay?
And you chose Ka2 because it actually, why did you select that?
Because if I read the question and it's asking for the anion concentration, which is S2 minus here. Okay? What is S2 minus? If they're asking for that, then it will equal the Ka2. Because by the time the second hydrogen comes off, those concentrations cancel, and S2 minus equals the Ka.
So what was the easy way that you said to do it, or like the stereo in the base thing? What?
Right there. They gave me 2 Kas. The second Ka is equal to the concentration of the S2 minus. That's the easy way. Doing absolutely no work.
But how would you know that? Just by looking at it?
Because that's what we're learning right now. That's how you know it. Now you know because we just worked it out. Okay? I worked it out so you could see why, but now you know, okay? Now you know that if they ask for the anion concentration of this acid, this diprotic acid, or triprotic acid, it will be equal to the last Ka.
So like if it, another situation, if we're asking for like pH, we just take
That would be different. That would be a whole different situation, and it would be more to that. Okay, but that would be a different situation, and I don't even think I'm going to ask you those kind of questions for diprotic acids. Mostly, what we're going to focus on for pH and everything is the monoprotic acids, and
So we don't have to do this. Is that what you said?
that's what I'm just saying. You don't have to do any work. That's all you have to do right there.
So it's just the last Ka.
It's the last Ka. That's your answer, which is an answer choice on that question. So I would choose that one. Just saying. Okay, now, here we go. Back to this. Okay? So before we get this started, this is what I want you to do so that we're not muddling around with all the concentrations and everything. I want you to find the concentrations of the acid and of the base and of the acid from the very start. Okay? So dilute everything, find the dilutions. Let's get those numbers. Okay? And then we will easily be able to answer all these next questions. Okay? And hopefully it will clarify some of the frustration you're having. Okay? So let's go ahead and tell me, once you find the concentration of B for the base right here, 0.3 times 10 divided by 20. And does everybody know why I'm setting these up like they are? If not, let me know so I can clarify that. That's right. So this 0.3 is the molarity of the base times the volume of the base divided by the total volume after I add 10 milliliters, which is 10 plus 10, it's 20. Okay? So what is that?
0.15.
Okay? What is it for C?
0.1.
And D?
0.075. 0.06.
0.6? Is that what you said?
Yes.
Okay.
0.06.
0.06. Thank you. Okay. And now for the dilutions of the acid. Okay.
0.0667. 0.075. And 0.08.
And E, I don't have it up here, but that will be 0.8? 0.8?
0.08.
Okay, perfect. Now look at D. Look at D base and D acid. What do you notice?
Hey.
That's the equivalence point, right?
Crappy.
That's the one where we reach the equivalence point. Okay. All right, so now we have all of our concentrations. Now we can easily set up our equations, okay? So we're starting with,
What are we looking for? pH?
I'm sorry?
It didn't say. Well, are we looking for pH?
pH.
Okay.
Let me see. Let me verify. Pretty sure that's what we're going to look for. Calculate the pH. Yes. Okay. So we're starting with, this is ammonia, NH3. It's a base. Okay. And we're going to react it with HCl, an acid. So with H plus. And it's going to produce NH4 plus in solution. Okay? Are we okay on that? That's the equation I'm going to use
So if we used
for the nope, sorry. Let's start over. Because it's not for the first one, is it? So for the first one, we're taking NH3 plus H2O because it's a base, and it's going to equilibrate with NH4 plus and produce OH minus in solution. Okay? Because the first situation, A, is just, we didn't add anything. It's 0. Okay? And the NH3 to begin with is 0.3 molar. Right? So because all I have is NH3, I have to establish the equilibrium of NH3. Because that's the only thing I have in situation A.
give a Ka or Kb.
Oh, sorry. The Kb equals 0, I'm sorry. I don't want to do that. 1.8 times 10 to the negative 5. It's a Kb. Not for this case, because this is a base, and we're finding OH minus. We will use the Ka later in this whole situation, but right now, for this one, we're going to use the Kb. Yes, I can. Not there. So you should be finding the pH.
The left side, these ones are the bases, correct?
The bases are these ones. These are the acids.
Oh, okay.
because NH3 is a base, and that's what we're starting with. And we're titrating it with an acid, HCl.
Wait, you said the ones on this side are bases? I mean acids.
These are the NH3, which is a base. This is the HCl, which is the acid. Okay? As your pH,
That's POH.
that might be a POH, but this is a base. Okay, that sounds more like it. That is the NH3. Okay, we'll come back to this page, but let's go ahead and look at how we did this. These are at 0, right? And hopefully you're seeing before if we didn't even have to do this, you could have just said this equals x squared over 0.3 without having to set up the whole thing. Because hopefully you're recognizing by now that this is going to, because those are at 0, it's going to be x squared over there, and this is going to be 0.3 minus x, and it's going to drop to negative x, and you're going to get x squared over 0.3. Okay? So my x equals what? Okay? I take the negative log of that, and my POH is equal to 2.63, and so my pH is equal to 11.37. So if you have a 0.3 molar ammonia solution, the pH of it should be 11.37. Okay? Okay, now, so that's easy. The start, because we didn't add anything. The question is, what is the pH of a 0.3 molar solution of ammonia? Right? That's A. Now in B, we're actually adding acid to this. So the acid will react with the NH3, the base. Okay? So, Patrick, what equation am I going to use?
NH3
Good.
plus H plus into
Do I have an equilibrium arrow? No, because I'm just saying the H plus is reacting with the NH3. This is not an equilibrium. Okay? I am pushing that over. So what is the, finish it, I'm sorry?
NH4.
NH4 plus. Good. That's it. Okay? That's my equation. Because it's a base reacting with an acid. If it was an acid reacting with OH minus, it would produce water. So you would add the water. But this case, we're not doing that. Okay? Okay. So this is my beginning situation. You guys have it all written down, right? What is for situation B here? NH3 is 0.15? 15. NH plus?
0.05.
Okay? And NH4
0.
is 0. Okay. In the end of this, am I going to have acid and base left over? Am I going to have concentrations of NH3 and NH4 plus? I will. So what equation can I use to find the pH? That Henderson-Hasselbalch. Okay? I can use the Henderson-Hasselbalch equation. Okay? Let's go back to this page up here. Okay, so in situation B, I will have concentration left over. Situation C, will I have acid and base left over?
Yes.
Henderson-Hasselbalch. Situation D,
No.
no. So I cannot use Henderson-Hasselbalch on situation D. Situation E,
You can just take
that's easy, right? That's the easiest one. Whatever OH is left over, I take it. All right. Okay? So hopefully this is already starting to become a little less frustrating than it was.
So NH4 is the acid, and obviously because it came to hydrogen, right?
It is the acid.
Just using the Bronsted acid. It's not. Is that
Yep.
what it is?
Use the definition of a Bronsted acid.
Bronsted acid.
What's that?
Yeah, okay.
Okay? NH4 is the acid, is the hydrogen donor, if I'm going back, so it's the acid. NH3 is the hydrogen acceptor, so it's the base. Okay? Whatever has more hydrogens is the acid. Minus 0.05, minus 0.05, this goes to 0, this becomes 0.10, this becomes plus 0.05, 0.05. So, pH equals pKa plus the log of the base over the acid. What's my pKa here? You need to find Ka.
5.56 times
5.5 times 10 negative 10. What's the negative log of that? There we go, 9.25. So my Ka here is 9.25 plus the log of the base over the acid. In this case, the base is what?
0.05?
Nope.
0.1.
0.1 over 0.05. So I have more base than I do acid, so that pH of this should be above 9.25.
So I'll do 0.63, right?
I'm sorry?
0.63.
Oh, log of 2. Yes. 0.06. What is it? 0.0. Okay, so my pH equals what?
That's natural log of 2.
Oh, that's right. I'm sorry? 9.5?
Yeah, 5.
Okay.
How
So,
do you know when, I'm sorry, how
go
do you
ahead.
know when to use the anti-log and the log, the negative log? Negative log is when you're trying to find the
Okay.
P of something.
So if I have a number like this, if it's a whole number, like 9.5, I need to use the anti-log.
So you're trying to go
If
back.
it's a decimal, I need to use the negative log.
Oh. Okay, so
That helps.
when you have, you said you have a whole number or what?
Yeah, when I not a whole number, but when I have a number larger than 1, let's say. Like a pH is, between 0 and 14. So if I have a number between 0 and 14, I'm going to take the anti-log. If I have a decimal, I'm going to take the negative log of that decimal to find the number, this number greater than 1.
So for this one, can we technically do pKb so we keep it right over the left? Log of acid over base.
To find the pOH,
Find the pOH.
you could find the pOH plus equals the pKb plus the log of the acid over the base. If you wanted to do that, you could. It's fine. And then you just take but this is the Henderson-Hasselbalch, this is it. Either way, you're going to get the exact same answer. So if you wanted to do that, but I don't want to confuse anyone. So,
Just forget I said that.
well, if you understand it that way, you're welcome to do that. Okay?
Because I'll forget pOH and
Okay. So, but this will help us. So the pH equals 9.5.
Wouldn't you also use the anti-log when you're like doing the algebra for it and you're trying to isolate something?
If I was
you're trying
doing
to go
this,
backwards?
if I was doing the Henderson-Hasselbalch and I was trying to solve for the ratio B over A, I would have to use the anti-log of whatever that pH is to get there. I'd subtract the pKa from the pH, and then I'd use the anti-log to find the base over the acid. For the algebra, yes. Okay? But in the case of when do I use the anti-log versus the log, it's when it's a number greater than 1, I'm going to use the anti-log. When it's a number less than 1, I'm going to use the negative log of. Okay? Okay, so this is situation B. For C, what is the equation I will use? Same one, NH3 plus the H plus, because I'm reacting the acid with the base. NH3 is reacting with H plus. Okay, so I'm going to use this equation. Why in A I didn't use this equation? Because there was no acid reacting with it. In that case, I used the equilibrium equation of NH3. Okay, but in this case, the H plus is reacting with the NH3 to produce NH4 plus. What is the initial concentration of NH3 that we determined from our dilution equations? 0.1 for C, 0.1, and of H plus? Oh, well, I just rounded it to 6, 7 because I ran out of room, but it's not going to matter. That's fine. Okay, so this is minus 0.067, which gives me 0. This is minus 0.067, which this is 0 to start, plus 0.067, 0.067. Okay, what is the NH3 concentration?
0.033.
Okay, now in this case, I have more NH4 than I do base. So if my pKa is 9.25, then my pH will be less than 9.25 or more than 9.25. Less, because I have more acid than I do base, right? So pH equals 9.25 plus the log of the base, which is 0.033 over the acid, 0.067. What's my pH here? 8.94? 9.5? You guys are so picky. That what don't matter? Well, the reason, we don't use a lot of significant figures because you have so many other things to worry about. And plus, the tests are going to be multiple choice. You need to find the closest answer, and the way you round something on your calculator might have been different than somebody else, and so the answers are essentially the same, just rounding differences, and so. Good. That's the best way to get the most accurate answer, right? So absolutely. But some people don't do that, so their answers come out a little different. Okay, so this is the pH. That's for C. D. What's the equation I'm going to use? NH3 plus H plus is going to produce NH4 positive. What is the initial concentration of NH3? But what is it?
0.075.
Okay, so these are my initial concentrations, right? Both of these are going to go to 0. And I'm left with NH4. What do I do now?
Now it's going to be NH4 plus.
Now I need to find the equilibrium. Okay, what is the question? How would I word this question to find the pH of this at this point?
Find the pH of S.
What is the pH of a 0.075 molar NH4 solution? That's the question at this point, because that's all I have. So
So it's plus water?
NH4, it's an acid, so it just dissociates into H plus OH, plus NH3.
So acid is
Just take a hydrogen off the acid. That's right, it just dissociates. If it's a base, react it with water
to create something in the way.
to create the OH minus. Okay? So 0.075, this is 0. NH3 is 0. This is minus X plus X plus X. Okay? So I didn't even have to do this. I could have just looked at this question right here, that concentration, and I could have said that 5.55 times 10 to the negative 5 equals X squared over that concentration of 0.075. Oh, 10. I'm sorry. 10.
Okay.
Sorry about putting 5 there. It's 10. 5.55 times 10 negative 10 is the Ka. So X equals what?
0.002.
And so my pH is the negative log of that.
2.69. Whoa. Drop.
That seems pretty low.
Yeah, that dropped. Yeah, that's way off. Samsonite.
That's some better French you're using there.
That's 5.1.
I'm sorry? 5.19. Okay. What's the X?
Yeah, 6.4 times 10 to the negative 6. Is that? Yes.
Okay. That's better. Okay, so we have a pH. So, what is the pH at the equivalence point of a 0.03, 0.3, what was it? Of a 0.3 molar NH3, of 10 milliliters of 0.3 molar NH3 solution, the pH at that equivalence point would be 5.19. This is the pH at the equivalence point. So if I was going to use an indicator, I wouldn't want to use an indicator that was up in the basic region, or at neutral. I would want to use an indicator that shows me the pH at an acid of concentration pH of 5.19. Okay? So choosing the indicator for this titration would be important. I couldn't just use any indicator. It would need to be one that shows me the acid, that it's acidic.
So the equation, the NH4 plus S plus NH3, is it like HA equals H plus plus A to the negative minus? Is it the same thing?
HA2 H plus A minus. It's exactly the same, right? What did I just do? A minus. Come on. Okay? H plus A minus. Yeah, it's the same. Okay? All right. Now for the easy one. Our favorite one. Okay? Well, once you guys start to figure this out, it's getting easier, right? Starting to see, trying to see how it all works, how it's all coming together. Okay? Okay, so for this one, I'm going to take NH3 plus H plus, and it's going to produce NH4 plus, right? What is my concentration? This is for E. What is my concentration of NH3?
0.06. 0.08. 0.02.
Oh, wait. So what am I going to do here? I was about to do it, but I want you guys to tell me. The smaller one is the one that goes to 0, right? 0.06 minus that goes to 0. Minus 0.06, that goes to 0.02. And this goes to plus 0.06, 0.06.
Does that only happen in these kind of problems? Where you just subtract from the smaller one?
I'm sorry?
Does that just happen in these kind of problems, the titration problems? Or
Yes.
you know, so many
That happens in
problems.
titration problems.
Okay.
We overcame the base. We overcame it, the concentration of it. So now, whatever the concentration of H plus that's left is the pH of this solution. So take the negative log of 0.02. Didn't we just do that earlier? Equals, what is it? 1.7.
1.7.
Well, last time it was negative log of the OH, so we subtracted it from the
Yeah.
That's right. This one's direct because it's the H plus. So we can find the pH directly. But if it was the OH minus, we'd have to find the POH and then the pH. Okay? Okay. Okay, guys, we'll stop there.